Right, and so our study so far of vector fields and path independence and using fundamental theorem of line integrals relied on this idea of f being conservative. And so what do we do if we think of if f isn't conservative? Can we prove it? What do we need to do this? We're going to attempt to answer this, but before we do that, we need to talk about a theorem. So there's a theorem that says, okay, if we have a vector field that is C1, so that's the definition of the vector field, and then we say that this vector field, if we know it's conservative, then we know that that D of f is symmetric. Okay, so D of f, just a reminder, that's the derivative matrix. Okay, so if it's conservative, we'll go through the proof for the case of n is equal to 3, and then we'll just leave it for the other ones. What we can say for n is equal to 3 is that if we have f equaling the gradient of a scalar function, the scalar potential function, so that means that this is, by definition, df, or del f del x, del f del y, and del f del z. Okay, then we can say, okay, well, the derivative matrix of vector field f, the derivative of vector field f would be equal to the derivative of the gradient of the potential function. Okay, and then this is going to be, and I'm going to use different notation. Okay, we're going to say that this is fxx, fxy, fxz, and then fyx, fyy, fyy, fyz. Okay, and then we have fzx, fzy, and fzz. Okay, and these are second order partial derivatives, which means by, okay, so then by Clairaut's theorem, you might have to look that up if that doesn't surface to the top of your brain right away. But we did discuss it last semester. By Clairaut's theorem, that gives us that df is symmetric. Okay. So that's kind of a nice thing. Now, as a corollary, okay, if we have that vector field that is still C1 and it's not symmetric, oh, that's kind of the contrapositive of our theorem. So if it's not symmetric, then we know that f is not conservative. Okay, so that's actually one nice way of proving that something is not conservative and therefore not path independent and so on and so forth. Okay. So then, just as a quick example, if we have this vector field, y comma 0, is this conservative? And this is the example that we actually saw in the very beginning in video 1 of this section. So if I look at the derivative matrix associated with vector field f, what I believe I get is 0, 1, 0, 0. Okay, and so this clearly is not symmetric, so that implies it's not conservative. Okay, so that's why in that example we were getting kind of things that didn't make sense. Our vector field wasn't conservative. Okay, so then now this kind of, I guess we still haven't addressed this fully. So there's this other idea about the derivative matrix being symmetric and conservative, and so before it was a one-directional thing. If it was conservative, the derivative matrix was symmetric. Well, is it true the other way around? So is the converse true? And so that I'm going to tell you, well, we're going to hold off on that until next week, and we need to get to some topology ideas to fully to be able to fully explain this. So more on this next time.